Okay, welcome back for another afternoon session. Our first talk is going to be by Fabian Zaiser, who's going to tell us about a library for verified Monte Carlo in Dafny'.
Yeah, thanks, Joe. So yeah, I'm a PhD student at Oxford, but in the fall I completed an internship at AWS where I worked with Stefan, Zetzsche, and Tristan on VMC, which is a Dafny' library for verified Monte Carlo algorithms. So, since not all of you might be familiar with Monte Carlo algorithms and probabilistic sampling, quick reminder. So probabilistic sampling means generating random samples from a desired probability distribution. This is important in various areas in computer science, such as cryptography and differential privacy. And it's hard to do correctly. And I'll give you two examples for this. The first one is the Fisher-Yates shuffle, which samples a random permutation of a list. And if you look at the Wikipedia article, it has a whole section on potential things you can do wrong and that people have done wrong in the past. Another thing is differential privacy, which also needs probabilistic samples from specific distributions. And this paper here describes an attack on differential privacy that was caused by a very subtle implementation error for a sampling algorithm that was proven correct on paper mathematically, but there was a subtle mistake in the implementation that completely destroyed differential privacy. So why is this hard to get right? Let me give you a simple example of why reasoning about probabilistic programs is difficult. So here we have a very simple sampler that returns 0 or 1. It only uses simple distributions like geometric, Bernoulli, binomial, and simple operations. So it shouldn't be too hard to figure out what the probability of returning 1 is, right? Well, it turns out it's 1 over pi. And that's a bit surprising because everything we do is like rational numbers. So where does this come from? And it turns out that what this program implicitly does is computing this infinite series, which just happens to converge to 1 over pi. And I think this illustrates why reasoning about probabilistic samplers is harder than like deterministic programs. And this is where the project Dafny' VMC comes in. So VMC stands for Verified Monte Carlo. Monte Carlo algorithms are sampling algorithms are an example of Monte Carlo algorithms. So this library provides a number of samplers for various distributions, including proofs of correctness that are formalized in Dafny'. And it's interoperable with Java. So you can call these samplers from Java, and the samplers will use the random number generator provided by Java. It's currently work in progress, so it's partially axiomatized. But it's already open source in GitHub, and you can check it out if you're curious. So what are the components of a sampler in Dafny' VMC? There's 5 parts. The first one is a functional model, like a mathematical description of the sampling algorithm. Of course, this has to be proven correct. But in practice, we want to use an imperative implementation that actually uses an external source of randomness, such as the operating system random number generator. And to relate this with the functional model, we need a proof of correspondence between the two. Of course, assuming that the external random source is correct. And we also have statistical tests in place, because not all the samplers are fully verified yet. In this talk, I'll focus on the first 2 aspects. All right, so how would we express functions that can return random values in Dafny'? Well, this seems difficult because Dafny's functions are deterministic. They give the same output every time you call them with the same inputs. So they need to take the randomness as input already. And the way we model the randomness is just with random bits, with probability 1/2 they're 0, probability 1/2 they're 1. And since we don't know how much randomness is needed, we just pass in an infinite stream of bits. Then the function can use these random bits to compute a random value, and it'll return the unused bits for future computations. So you can think of the randomized functions in Dafny' as bitstream transformers. In code, this looks something like this. So this bitstream type is an infinite sequence of booleans. And if you wanted to model a fair coin, you could just take the first bit from the bitstream, return that, and as the second component of the return value, you'd return the rest of the bitstream. So the original shifted by 1. This works fine, but it's a bit error-prone to pass these bit streams around all the time. So it's nice to have an abstraction for this. And in fact, Joe Hurd introduced such an abstraction, which we call the Hurd monad. And this way you just need to use a small set of combinators, which are coin, return, bind, and while, to express all the samplers in the library. So in code, it looks like this. The herd type, herd monad, is a function that takes a bit stream as input and returns a value and a remaining bit stream. And the primitives that I mentioned look like this. So coin is basically the same as before, except it now uses this herd type. The combinator return just takes a value and deterministically returns it without touching the bit stream. Bind does composition. And finally, we need some construct for looping, which is called while, which operates on a state of type A. And as long as the condition is satisfied of the state, it transforms it with the body function. All right, so this shows how to include randomness in Dafny, but how can we actually reason about the probabilities of those random values? For that, we need some probability measure. And we put those on the bit streams because the bit streams is where the randomness comes from. And the probability measure we put on the bit streams expresses the idea that all the bits are independent and uniformly distributed, so probability 1/2 of being 0 and 1. And Herd proved that this probability measure on the bit streams makes them a probability space, which we have currently axiomatized but want to prove in the future. And in code, this looks something like this. We have this prob function, which takes a set of bit streams and returns their measure. And for convenience, we have this function probability mass, which takes a probabilistic computation, returning values of type A, and is also given a result value, and returns the probability that we get this result value from the computation. In other words, takes the probability measure of all the bit streams where the result equals the result we care about. And with this probability mass function, we can express the correctness of the coin example. So we can say that the probability mass of coin returning false is 0.5 and the probability mass of coin returning true is 0.5. Now I want to talk to you about my project during the internship, which was to implement and verify the Bernoulli exponential distribution. And I think this is a nice example because it illustrates many of the challenges we faced. So on the surface, it's quite simple. It returns true with probability exponential of minus gamma, assuming that gamma is between 0 and 1. But this is actually quite tricky because we can only use rational numbers in the computations. But the probability we get in the end is irrational. In fact, this distribution is the source of irrational probabilities for all the samplers in the library. And it's a building block for many important distributions, such as the discrete Laplace distribution and discrete Gaussian distribution, which are important in differential privacy. So in pseudocode, the sampler looks something like this. So we get the gamma parameter as input, and we return a Boolean, true or false. And we have a state with two variables. The first one's a Boolean, a, and the second one is a natural number. And as long as a is true, we increase k by 1 and resample a from a Bernoulli distribution with the parameter gamma over k. And finally, we return whether k is odd. So why would this give you this exponential probability? So just to give you a rough idea of how this works, first of all, let's look at the probability that the k we have at the end of the loop is greater than some number n. For this to be the case, we need to have had n loop iterations, and in each iteration, the probability of a being true is gamma over k. So to have at least n iterations, we get this product, gamma over 1 times gamma over 2, and so on. So overall, gamma to the n over n factorial. So the probability of having exactly n iterations is the probability of having at least n minus 1 and not more than n. So we take the difference between the two probabilities. And finally, we care about the event that k is odd. So we need to sum over all odd numbers. And if you rearrange this a bit algebraically, you see that this is just the power series for the exponential function. All right, so how do we do this in Dafny'? Well, we have this function that returns random booleans. we can formulate this precondition on gamma as follows. And then we have this while loop, which operates on a state that is a pair of booleans and natural numbers. And the loop condition just says that the boolean should be true. Then what does the body do? The body increases k by 1, and then samples from the Bernoulli distribution with the gamma over k parameter, and then takes the result and combines it with the k that we computed for the next iteration. The initial state is a being true and k being 0, and in the end we return whether k is odd. Okay, so this looping construct is quite important for this distribution. So how would we express this in Dafny'? Well, the first idea might be something like this. So this while function takes a condition and a body statement, a body function, and given a state, if the loop condition holds, we enter the loop, run the body transformation on the state, and then recurse, running the loop on the result again. And if the loop condition is not satisfied, we just return the initial state. So this seems natural, but if you try this in Dafny', it complains and says we cannot prove termination, because this recursion may not be bounded. And this is a problem, because many samplers require loops. So rejection sampling, for example, is a common technique, and that requires a loop. In fact, it's even more fundamental. If you look at the uniform distribution on 3 objects, you want a probability of 1/3, but you cannot get that with a bounded number of bits. Because if you have k bits, then you can only get probabilities of the form something over 2 to the k. So you can't get a third. So the samplers may not always terminate, but they always terminate almost surely. But Dafny' can't reason about almost sure termination. So what do? Our idea is to track non-termination in the probability monad type. So we change our probability monad as follows. So this was the old version, which returns a pair of A and the remaining bit stream. And instead we return a result type, which can either be diverging, if the computation doesn't stop, or it can be, again, a pair of a value and the remaining bit stream. And all the combinations we had before, we can define just fine. I won't show you the definitions. And now we can also define, and this allows us to talk about the probability of non-termination and to state that the probability of non-termination is 0. All right, with this in place, we can actually define while loops properly. And first, we define a while loop with a bounded amount of fuel, so where the number of iterations we can do is bounded. So it takes an additional argument, fuel, and we first check whether the fuel is 0. For out of fuel, in that case, we say it's diverging, we bail out. Otherwise, if the loop condition is violated, we stop the loop and return the initial state. And otherwise, we do the same thing as before, recursing, but now decreasing the fuel by 1. So this is just normal recursion. And Dafny' can prove that it terminates. Now, how does the unbounded while loop work? The idea is that for a given initial value and a given bit stream, we check whether there is an amount of fuel for which the bounded loop terminates. If that exists, then we just take that bounded loop, and otherwise we diverge. So this shows how to implement the while loop, but how can we actually reason about the probabilities arising from it? So how can we prove that the loop produces a result with a probability p? And the idea is, again, to reason about the bounded version first, where you can just use induction, and then take the limit as fuel tends to infinity. So, for example, we use this lemma, while probability, which is currently axiomatized, but we want to prove it, which takes the condition, loop body, initial value, the result we care about, and its probability. And we have to verify that the result violates the loop condition, because otherwise we would keep looping on it. And then we look at the sequence of the probability masses of the bounded loop as the fuel increases. And if that converges to p, then this lemma tells us that the probability mass of the unbounded loop for yielding the result is also p. And this required formalizing some real analysis in Dafny', for example, limits. So with this lemma, we can prove the correctness of the Bernoulli exponential distribution, where we again have to use a limit argument. So this proves that the probability mass of Bernoulli exponential returning true is the exponential of minus gamma, and analogously for the false case. And for this, we had to define the exponential function in Dafny', which is currently partially axiomatized. So yeah, in summary, Dafny' VMC is a cool project, at least I think so, for samples of various distributions with proofs of correctness. You can check it out on GitHub. And in particular, I think the verification of the Bernoulli exponential distribution is interesting because there's two challenges. We had to formalize some real analysis in Dafny', for example, limits in series. And there's interesting research on probabilistic loops and non-termination to be done. Thanks for listening, and I look forward to your questions.
Thank you. Very interesting. I was wondering, you have been able to encode to make an API that has everything that, I suppose, everything that you need in order to reason about probabilistic programs. Mm-hmm. But I was wondering if Tristan were designing Dafny' now, would you suggest that he designed it differently in order to be able to express what you need? Or is it fine to do it the way you did it?
There's one main limitation that we can't do yet. It again has to do with non-termination. So I showed you how to deal with non-termination for the functional model, so the mathematical description. But for the imperative side of the sampler, we can't do something similar. So there we cannot prove termination and can just prove partial correctness. So if there was a way to tell Dafny' this function doesn't, this method doesn't terminate, it only terminates almost surely, that would be nice, but then it's not clear how to exactly encode that in Dafny' and how such a property in Dafny' would look like. But that would be cool.
Sorry, I had to miss most of your talk, but I have a question on partial correctness. What is partial correctness of a sampler? Or of...
Yeah, so in what I just said, yeah. I meant that if you have a method that samples, like an imperative method that uses an external source of randomness, so that is not the pure mathematical functional model, then there it can happen that it doesn't terminate. If you have a loop, and you always get
the sampling method, you mean?
Yeah. So.
Okay. No, that answers my question. Yeah. Thanks.
Okay. Maybe we can thank the speaker and move on to the next.